So why is R naught? Okay, what happens when R naught is equal to 0? If R naught is equal to 0, then what? Then you consider some y n. R naught is equal to 0. You consider some y n where okay, R naught is like that. Okay. You've defined a function R on a space Y where R maps Y to the largest, to the supremum of the radius of a ball centered at Y, such that the ball is contained within some open set which contains Y. And then you let R naught be the infimum, of Ry's for Y's in the set Y. Okay. So what this means is that R naught is a radius of a ball, is a radius such that for every point Y in your space Y, you can draw a radius, a ball of radius, say, just slightly less than R naught. So like R naught over 2. And that ball will be wholly contained within some open set which contains your point. So we will be working with R naught over 2. Just to be safe. So you have three cases. If R naught is equal to 0, that means that for any positive integer n, we can find some yn such that R of yn is less than 1 over n. So consider this sequence yn. Because y is compact, we can find some convergent subsequence of this yn. And by definition, this yn has the r of this yns, the r of these yns goes to 0 because it's less than 1 over n for each n. So less than 1 over n for each. So if you let y naught be the limit of a convergent subsequence of this sequence, which is given by compactness, we consider that y naught is within some open set V alpha. Y naught is contained within some open set V alpha. So in particular, we can draw for some epsilon greater than 0, some epsilon ball centered at y naught. Okay. Then what do we do now? We have this epsilon ball centered at y naught. And we also have this convergent subsequence which converges to y naught. So what do? By convergence, you can get epsilon over 2 away from y naught, and then draw an epsilon over 2 ball, which is contained within the epsilon ball of y naught, which is contained within the open set VA, which means that in some sense the epsilon ball centered at y naught is propping up, it's expanding, it's making sure that Ry's of the convergence subsequence maintains above epsilon over 2, which contradicts the assumption that the convergence subsequence has R's that go to 0. Okay. So that's a contradiction. We do not have R naught is equal to 0. Now, suppose R naught is some positive real number. So what does that mean? That means that, okay, to be safe, I don't know, maybe I'm not stupid or something. Yeah, because you're taking supremums and infimums. Yeah, so it's like a little bit dangerous. So just to be safe, you pick R naught over 2, R naught over 2, R naught over 2, just to be safe. So for any point y in your space y, you may draw a ball of radius r naught over 2 centered at that point y, and that ball will be contained within some open set which contains the point y. We will show that we must have a finite open subcover. I must have a finite subcover by means of contradiction. So we suppose that that is not the case. So we pick some arbitrary point in the space y, arbitrary first point, and then we draw the r naught over 2 ball centered at that first point. Okay, but now we said that hey, we cannot have we cannot have a finite subcover, so that means that y is necessarily not a subset of our ball. Okay, because our ball is open. So what do we do next? Okay, what do we do next? We remove that ball from y. We remove that ball from y, and then now we are left with y with the ball removed. We pick some second point from that new space with the ball removed, and then same thing, we can draw the r naught over 2 ball centered at r2 y2, and then the union of these two balls cannot contain y because y has no finite subcover. So again, you remove the second ball from the space y with the first ball removed, and you continue this, adding points, remove considering a ball around that point, noting that y cannot be contained within the union of all the balls that you have constructed, and so remove more and more balls from y, but the union of these balls not containing y. So you have a sequence of yns from this construction. Can you have a convergent subsequence from this sequence of yns? No. Why? Because each term, any two terms in the sequence are at least r naught over 2 away from each other. So it contains no Cauchy subsequence. And because none of the subsequences are Cauchy, and convergence implies Cauchy, not being Cauchy means that the sequence has no convergent subsequence, which contradicts the compactness of y. What does that mean? That means that we have a contradiction. So necessarily we have a finite subcover. If r naught is equal to positive infinity, that means we can draw a ball of any size that we want, and it will be contained within some open set. So we just fix any positive integer and we can repeat the argument and show that it has a finite subcover. Isn't that crazy? Corollary. Let xd be a metric space, and let k1, k2, k3 be a sequence of non-empty compact subsets of x, such that k1 contains k2, contains k3, and so on and so on and so on. Then the intersection of the kn's is non-empty. Why? Vn, you define Vn to be K1. Vn is defined to be K1 remove Kn. And if the intersection is empty, the union of Vi, the union of Vi is equal to K1. The union of Vi is equal to K1, yeah? But it's also the union of K1 remove Ki. K1 remove the intersection of all Ki. Non-empty compact subsets of X. Suppose they have empty intersection, then the union of K1 remove Ki. K1 remove Ki is equal to K1. Why? Okay. But K1 is compact. So you only need a finite number of VIs. You only need a finite number of VIs to cover K1. Then the point is that K1 is contained within. Okay. Whatever, I don't care. What's the idea? The idea is that you have if they are compact, then you can find. Okay, you consider. Is K1 remove Ki. This is compact. This is compact. This is open. Open? Yeah, sure, it's open. Sure, it's open. Let Y be a compact subset of X. Y, X, and equals K1. What are we doing here? K1 be a subset of X be, and then Ki. K1, Ki is closed. Closed. Close it now. K, so that is open. That is so Vi is a bunch of opens. Okay. So what else? Why the buttons? When the bad things from the good people. Then what do you have? The problem is because the problem occurs when contradiction arises when because we have K1 is compact only requires a finite amount of open sets which are defined in terms of the other compact KIs. The compactness of KIs gives us the openness of K1 removed, which we use to cover K1. So if we consider the maximum finite set F, then we get our empty compact set, which is a contradiction because we assume that all the KIs were non-empty. Compact if and only if let XD be a metric space, then what if Y is a compact subset of X and Z is a subset of Y, then Z is compact if and only if Z is closed. Why? If Z is compact, then there exists a convergent subsequence or any sequence. So And xt have the property that every open cover of X has a finite subcover. Show that X is compact. Let xt be a property, have the property such that every open subcover has a finite subcover, and then X is compact. Okay, so suppose we have a metric space with a property, and for contradiction, we show that we suppose that X is not compact. It's not sequentially compact. Then you have a sequence with no limit points, i.e. no convergent subsequence, because it is not compact. So there exists such a sequence. So for all X in X, there exists an epsilon such that the epsilon ball about X contains only finitely many elements of Xn. Why? Because there's no limit points. Suppose there exists an X such that for all epsilon greater than, okay, there's infinitely many elements. Then let N1 be JB. So you construct a limit point. You construct a limit point by considering a point with so there exists for all X there exists a blah 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 only finitely many. So you consider the union of open set. So you consider a finite cover if you have like open cover implying finite subcover, then the finite subcover has finite elements, and the balls, the open sets, you have a union of finite sets. You have a finite union of finite sets, but you're trying to cover a infinite space. So that's a contradiction. Blah 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 blah. Theorem: continuity preserves convergence. F is continuous at x naught. Blah 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 blah. Continuous. Open set preserves open sets. Pre-image preserves Closeness, pre-image preserves openness. Composition preserves continuity. But non-continuous functions may compose if continuous may compose to give you a continuous function. The inclusion map is continuous. Inclusion map is continuous. The coordinate functions are continuous. The coordinate functions are continuous. Polynomial. Polynomial of two variables is continuous. And yes. Yeah, we construct a sequence of in f of k. We construct a sequence yn in the image of k under f, and then we consider a sequence xn such that each xn gets mapped to a yn under f for each n. Since k is compact, xn has a convergence subsequence xnj. And let's call this limit x0. And this x0 is contained within k. So f of x0 is within f of k. But f is continuous. So that means that the limit of f of x of nj, the limit of f of the subsequence goes to f of x0, which is in f of k. What does it mean? What does that mean? How's it compact now? Oh, because it has a convergence subsequence. Oh, yeah, convergence subsequence. Yeah. Because f of x and j forms a convergence subsequence in f of yn. Forms a convergence subsequence of yn. Continuous maps preserve compactness, maximum result. Let xd be a compact metric space and let f from x to r be a continuous function, then f is bounded. Furthermore, if x is non-empty, then f attains its maximum. Is this extreme value? Extreme value theorem. That's crazy. Maximum result is extreme value theorem. And all you need is that x be a compact space. You don't need a compact space. Uniform continuity. If it's uniformly continuous on a compact metric space, then it is. If it is continuous on a compact metric space, if it's continuous on a compact space, then it's uniformly continuous. If and only if. That's crazy. And only if. Oh yeah, of course, because uniform continuity implies continuity. That's crazy. That's so crazy. So crazy. Connected. And only if it's there exists disjoint non-empty sets, equivalently, we have a non-empty proper subset which is simultaneously closed and open. Simultaneously closed and open. It's clopen. That's crazy. It's clopen. Connected. Connected. Continuity preserves connectedness. What am I doing? Continuity preserves connectedness. Let f from x to y be continuous, and let E be a connected subset of x. Then f of E is also connected. Why? If f of E is not connected, then you have two non-empty subsets of f of E. Okay, you have two equivalent definitions of discontinuity. You could be discontinuous if you have a proper subset, which is not the empty set, which is closed and open. Or you could have two disjoint open sets whose union is equal to your entire space. The union of two open sets of your entire space. So, what do we work with now? We want to show that f of E is connected, f is continuous, and we want to show that f of E is connected. Suppose it is not connected, then consider disconnected if you have two non-empty subsets of f of E such that they are disjoint and their union is equal to f of E. disjoint, and that union is equal to f of e. But then, since f is continuous, the pre-image of v under f is open, the pre-image of w under f is open. So that is equal to e. That is equal to e. And then it's joined. Okay. That means that you have open sets which map to E to disjoint. That means that E is not connected. That means E is not connected. That's a contradiction. So that means that we cannot have f of E be disconnected. That means that f of E must be connected. Really, intermediate value theorem. Yeah, because connected subsets of the real numbers is at interval. Connected real subset at interval. The arbitrary union of connected sets is I don't care about this one. I don't care about this one. I don't care about this one. Topological spaces. Oh shit, so much. Should I even read this? It's- Shit, that's the order topology. That's the order topology. That's crazy. That's crazy. This is the order topology. Why the fuck have I learned this before? That's crazy. That's crazy. Oh. The order topology on R is equal to the metric topology on R. This shit is okay. Let X be an uncountable set, and let F be the collection of all subsets E in X which are either empty or cofinite, meaning the complement of E is finite. Complement of E is finite. Means that this is the cofinite topology on X, which is not Hausdorff in a sense, and is compact and connected. So show that if X is in any oh my god. If it's not Hausdorff, then it's not metrizable. That's it. Do. V or V. Yeah, because what we're doing now, we're showing it as a fucking topological space. Doing it as a topological space. Oh, okay, whatever. This is enough. If it's cofinite, then both V prime and W prime are finite. So sure. The cofinite topology on uncountable X is not Hausdorff. Suppose for contradiction it is Hausdorff. Then we fix some element X in X, and then for all Y that which is not X, there exists a neighborhood in exists a neighborhood in X, there exists a neighborhood in W and Y in the W of Y, such that they are disjoint. So X is not in V. X is in V. X is in V, Y is in W. So X is in, so consider X not in V prime. V is equal to X. Remove V prime, W is equal to X. Remove W prime. V prime and W prime are finite. W is V prime and W. W is V prime and W. W is a subset of V prime. And similarly, V is a subset of W prime.